Welcome back to week 6 of pre-calculus. We continue our study of exponential functions. And today we'll look at the compound interest formula. Consider the following situation. You invest an initial amount of $P for T years with an annual percentage rate R, with interest compounding multiple times per year, N times. We claim that the formula that determines the price of the portfolio after T years is this: P times 1 plus R over N raised to the power NT. Let's explain this formula. So we invest an initial amount of $P, and within the first year, after the first period, we end up with what we had before, P plus P times our interest. The APR, the annual interest rate, is R, but because it's compounded multiple times per year, N times per year, it needs to be divided by N. That is P times 1 plus R over N. After the second period, within first year, we're going to have what we had before, P times 1 plus R over N, plus P times 1 plus R over N times R over N, our interest that we earned. And of course, this is P times 1 plus R over N squared. After N periods means 1 year, because we divide 1 year into N parts. We're going to have P times 1 plus R over N to the power N. After T years, we will have P to the power 1 plus R over N to the power NT. You can establish this the same way we established the formula for N periods. The central question for us is this: what is better for me as an investor? 10% interest rate compounded once annually, or 5% compounded semi-annually, every 6 months? Or perhaps compounded quarterly at an interest rate of 2.5%. Which of these options is better for me? With which of these options will I make more money? Let's consider a simple example to answer this question. Let's say we invest $1,000 with an interest rate of 10%, but we don't yet determine how often we compound it. Let's see what's going to happen. Let's say we compound annually. Well, if we compound annually and invest for 1 year, we're going to earn 1,000 plus 1,000 times 10%. And of course, that's $1,100. What if we compound twice a year? Once after 6 months with an interest rate of 5, and after another 6 months, again with an interest rate of 5. Well, after 6 months, I get $1,000 plus $1,000 times 5%. That is 1,000 plus 50, $1,050. That's how much I'm going to have after 6 months. Now, after another 6 months, I have my initial amount, 1,050 plus 1,050 times 5%. If you do the computation, that's going to be $1,100, well, $1,102.50. That is more than $1,100 that we get when we compound once. You can verify if you do 4 computations for quarterly compounding. That after the first 3 months, you will get 1,000 plus 1,000 times 2.5%. That's going to be $1,025. After another 3 months, you're going to have $1,025 plus $1,025 times 2.5%, whatever it is, and 2 more computations. You will end up with $1,103.81. And that's greater than the sum that you get when you compound semi-annually. It seems like the more frequently you compound, the more money you get. In particular, you could compute compounding daily, right, with an interest rate. So here the interest rate is 10%. Here the interest rate is 5%. Here the interest rate is 1/4 of 10, which is 2.5. Here the interest rate is 10 over 12%. And here the interest rate is 10 over 365%. Differences aren't big, but certainly the more frequently you compound, the more money you get, which is very interesting. And you might wonder if there is a limit to this gain. What happens if I keep on increasing the frequency of my compounding? What if I compound not daily, but every hour, every minute, every second, every millisecond? Interestingly, there is a limit. Let's say we look at the situation when we invest $1 to make the computation easy. Remember, the formula is initial amount P times 1 plus R over N to the power NT, where again, P is the initial amount. In our situation, it's $1. R is the APR, annual percentage rate. N is the number of times we compound per year. And T is the number of years we invest for. So in our situation, P is 1, let's say we invest for 1 year, so T is 1, and let's say the annual percentage rate is 100%, so R is 1. We are only interested in analyzing what happens when N increases without bounds. N is the number of times we compound per year. Annually means N is 1, semi-annually means N is 2, quarterly means N is 4, monthly means N is 12, daily means N is 365, hourly means N is 365 times 24, once per minute means N is 365 times 24 times 60, and once per second means N is 365 times 24 times 60 times 60. This is the formula used to compute the price of the portfolio obtained from this formula. Again, P is 1, T is 1, R is 1. We get 1 plus 1 over N to the power N. Plug in different values of N, we see that we get different amounts. And if you view this as usual annual investments, the rates are actually not what they are if you view them as frequent, with frequent compounding. For example, look at these $2. This is truly an annual percentage rate of 100%. But look at this $225, $2.25, $2.25. That actually corresponds to an APR of 125%, because our original investment of $1 grew by 125% to get to $2.25. For quarterly compounding, we get an APR of even greater, 144%. For an APR for compounding done once per second, we get an APR which is much greater than 100% that we originally invest. We get the APR of 171%. So looking at the numbers, so again, compounding more frequently does result in the price of portfolio being greater. The more frequently you compound, the greater the price of your portfolio will be. But there is a limit. If you look at the numbers in the last column, 2.25, 2.44, 2.61, 2.71. In the last 4 rows, the 2 decimal digits after the decimal point stay the same. In fact, in the last 3 rows, the 3 decimal digits after the decimal point stay the same, 718. In the last 2 rows, the 4 first decimal digits after the decimal point don't change, 7182. And the same here, 7182. That is a strong indication that this quantity limit of 1 plus 1 over n to the nth power, when n goes to infinity, has a limit. Because as n increases, more and more of the decimal digits after the decimal point stay the same. In fact, this is a very special number discovered by the Swiss mathematician Leonhard Euler. He called that number E, and it's defined as a limit of 1 plus 1 over n to the power n. It is roughly 2.718282. So you can get an interest rate. To answer our question, the maximal possible interest rate that you can get is the number E minus 1 times 100%, which is roughly 171%. When does this occur? This occurs when we compound continuously. What does that mean, continuously? It means we take a limit of the frequency of compounding going to infinity. And in fact, if we take a limit of that thing, 1 plus r over n to the power nt, as n goes to infinity, we will simply get p times e to the power rt. That is compounding continuously. You can't get more than that. In particular, after 1 year, you will simply get pe times to the power r. In this particular example where p is 1, r is 1, and t is 1, p is 1, t is 1, and r is 1, we won't get more than e dollars. No matter how frequently we compound. You may compound as frequently as you wish, every millisecond, every nanosecond. You will not get more than e dollars, roughly 2.72. That's a pretty interesting fact, because at first it seemed like increasing frequency of compounding gave us a great boost. The more frequently we compound, the more money we earn, but unfortunately, no, there is a limit. You can't earn more than if you were compounding continuously. You can't earn more than this. If you invest an initial amount of P and an annual percentage rate is R, no matter how frequently your bank compounds your interest, you will not earn more than this. P times e to the power RT. This gives rise to the following definition. We say that the function is continuous growth or continuous decay if it is an exponential function of the form a e to the power rt. Here a is before the initial value, the value of our function at 0, right? F at 0 being a e to the power r times 0 is simply a e to the power 0. E to the power 0 is 1, so we get a, the initial value, initial amount. R is the growth rate, the factor by which f grows or decays every unit of time. That's also easy to check. If we compute f at t plus 1 over f at t, that'll be a to the power e to the power r times t plus 1 over a to the power a e to the power rt. That is a e to the power rt times e to the power r over a e to the power rt. A and a cancel out, so do e to the power rt, and we are left with e to the power r. And so clearly f at t plus 1 is f at t times e to the power r. And this explains that if r is greater than 0, our function grows. And if r is less than 0, our function decays. Let's see why. If r is greater than 0, what do we get from this formula? F at t plus 1 equals f at t times e to the power r. Well, because r is greater than 0, e to the power r is greater than 1. After all, the graph of e to the power r, it's the usual exponential function. It passes through the point 0, 1, and once the argument is greater than 0, the function is greater than 1. Therefore, this is greater than f at t. So our function is indeed growing. The greater the argument, the greater the value of the function is. For r less than 0, we got the opposite situation. F at t plus 1 being f at t times e to the power r. Because r is less than 0, e to the power r is less than 1. Again, that's easy to see on the graph. When the argument is less than 0, the function stays below the line y equals 1. Therefore, in this case, we have our function decaying. F t times e to the power r will be less than f of t. So r greater than 0 implies f at t plus 1 greater than f at t. So f is increasing. And r less than 0 implies that f at t plus 1 is less than f at t. Therefore, f is decreasing. That is the definition of continuous growth and decay. Every time you see the word continuous, it means the base of your exponential function is e. So you kind of lose this freedom of choosing different bases b. Remember, we used to have a times b to the power t. You could use b anywhere between 0 and 1 and anywhere greater than 1, but now the base is fixed to be e, but you have this special factor r. In fact, e to the power r is b. So it's the usual exponential function. It's just that when r is greater than 0, b will be greater than 1. Remember, b here is e to the power r. And when r is less than 0, b, which is e to the power r, will be between 0 and 1. In this context, t is understood as time. And what's left for us to do is look at these two examples. A person invested $1,000 in an account earning a nominal 10% per year compounded continuously. How much was in the account at the end of the year? We know that if compounding occurred only once per year, they would have ended up with $1,100. We already made that computation on the previous page, $1,100. But if we compute with continuous compounding, we're going to have the formula P at t equals 1,000 initial amount e to the power 0.1 times t. That is how much money is going to be in the account after t years. So after 1 year, we have P at 1, which is 1,000 times e to the power 0.1. That is roughly, you could use a calculator, that is roughly $1,105.2. That is greater than $1,100. And that is the absolute maximum that you could get, no matter how frequently you compound. So of course, with continuous compounding, you get more than with compounding however frequently. Definitely more than compounding just once. We end up with $1,105.20. And in this last example, we have this radioactive gas, radium-222, which decays at a continuous, I'm not sure it's gas, I apologize, maybe it's not gas. It's a radioactive isotope, radium-222, and it decays at a continuous rate, again, continuous rate of 17.3% per day. How much will 100 milligrams of radium-222 decay to in 3 days? What is the formula governing the amount of radium? If t is time, and A of t is the amount of substance, in our case radon, left after T days, T is measured in days. This is measured in milligrams. Then A of T is the initial amount, 100, e to the power. Unfortunately, many students would simply write 0.17 e to the power 17.3% or 0.173t. But that would mean radon is not decaying, it's growing by 17.3% every day. To make it into decay, we have to put a minus. Remember, decay occurs when the continuous percentage rate, R, is negative. So we have this formula, and therefore after 3 days, the initial 100 milligrams of radon-222 will decay to AF3, which simply is 100 times e to the power negative 0.173 times 3. That is roughly 59.5 milligrams. If you were to forget the minus sign here, if you were to take a plus here, you could correct yourself when you obtain here a number greater than 100 milligrams. That would have told you immediately that your radon is not decaying, it's growing. And at that point, you could realize something was wrong. So what is wrong is the minus. All right, that finishes this example, and this finishes this week. We will talk about exponential functions more in the future. Thank you.